Yeah, is it good now? Okay. Yeah, so originally I was asked to talk about many-body localization, and I kind of, well, first of all, I gave many talks about this, and then if I would talk about it, it would be basically sort of a negative talk, like saying about the problems with theories. And I think the main issue, I mean, I can say with, so whether there is localization or not, or whether there is ergodicity or not, it's unsolved. It's one of unsolved problems, and as far as I know, no one really approached proving or disproving like ergodicity or KEM in many-body systems. But I can say with great level of confidence that existing theories of many-body localization are simply incorrect. Like RGs are incorrect, and numerical analysis is incorrect, like assumptions are incorrect. And the main issue is misunderstanding, the general misunderstanding of what quantum chaos is. So mostly people thought about quantum chaos as random matrix theory, as probably many of you heard about, or eigenstate thermalization hypothesis, and this implies ergodicity or thermalization. So there was an idea that we have basically either integrable systems or ergodic systems. And then if we introduce disorder or something else, we can have a transition from integrable to ergodic. But this is incorrect, and we actually know it. So if you go like to the street and ask, what is chaos? Like just ask random people. I mean, probably most common answer will be tornado, right? Or some, I don't know, hurricane. And these systems are as non-thermal as one can imagine. And moreover, these systems are extremely close to integrability. So if you take systems which are strongly non-integrable, then we usually have hydrodynamics like water in a glass. I mean, anyone will tell you they're not chaotic. Of course, they maximize entropy, we know, thermodynamics and so on. But what I'll try to maybe tell you today is that the transition from integrability to thermalization is actually very complicated. We know it from small systems, right? We know that there is a KM theory which tells us that we first break integrability, then we have this complicated mixed phase space, and only then we go to ergodicity. And there is sort of a buffer region in between. And I'll try to maybe at least, if not convince, but at least show some good indications that this story exists in many-body systems. So we always have this buffer region and so on. And once you realize that, you immediately see that why many like theories of MBL is simply incorrect. So maybe I'll say something about localization at the end. If I don't have time, it might be a good topic for discussion. As I said, I'm not claiming we disprove MBL or the other people, but we can definitely disprove theories of MBL. So since it's a long lecture, I thought that maybe I will tell you first, in the first half, about adiabatic transformations. I'm working personally on them over 20 years. I first, like, when I was a postdoc at Harvard, I started thinking about Kibble-Zurek mechanism. And then the more I work, the more you discover. You basically now, you can see them everywhere. And then I thought I will first show where we can see adiabatic transformations, like whether we talk about perturbation theory, WKB, Schrieffer-Wolff transformation, Born-Oppenheimer, Floquet theory, and so on. Of course, I will not mention all of them, and actually some of these things are related to earlier lectures today and yesterday. But still, I'll give you some flavor of what these adiabatic transformations are, what's the adiabatic gauge potential generator of these adiabatic transformations. And then in the second half, I will tell you how we can relate them to chaos, and I will not distinguish quantum and classical chaos because basically there is no difference. Like in this air, you don't really care whether collisions between atoms are quantum and classical. Okay. So I'll start from perturbation theory. And please ask questions. So that's basically first course in, I don't know, undergraduate quantum mechanics. We start from some Hamiltonian and some perturbations. Well, let me for now assume there are no degeneracies because I don't want to go into all details At the end, you will see none of those matters. And then usually, of course, we study corrections to energy spectrum, and we study corrections to wave functions. And I will be more interested today in corrections to wave functions. So what we usually say that psi n will be, say, n is like unperturbed state. Instead of naught, I will just use this plus. And if I make sign arrow, please forgive me. So I'll get m e n over e n minus e m times m times lambda. Instead of epsilon, we use lambda because I kind of got used to this notation everywhere. So lambda is a parameter which deforms the Hamiltonian. So now I would argue that what we are really studying is a Hermitian operator, which is a generator for adiabatic transformations. Let me just formally define A operator with matrix elements n and m is equal to I h bar d lambda, guess, right, m n, m d lambda n. Right. So, and I can read the answer from perturbation theory, right? Because essentially I'm asking what are the overlaps of perturbed eigenstate psi n with unperturbed states, right? So I just need to take this derivative with respect to lambda, and I have an answer. It's I h bar mv n over en minus em, right? So it's immediately clear that this is a Hermitian matrix, right? Because if I take complex conjugate, I'll change sign here. Well, this is Hermitian operator, so I switch m and m. But then I need to switch energy denominator, and this will cancel this minus sign. So this is Hermitian operator, which is always defined for finite dimensional matrices, and I assume I am dealing with continuous transformations. Like nothing breaks, and so on. So you actually, we know this. In some examples, we know this operator very well. So let me assume that what I'm doing is just I'm translating the system, right? So I'm just physically taking a box and make a translation. Then my psi n depends on x minus lambda, right? So lambda is a position of the box. Then this a lambda, it's a derivative operator. It's I h bar d by d lambda, which is the same as minus I h bar d by dx. And this is nothing but the momentum. So you see explicitly, yes, it's Hermitian operator, and you can even see why I included I h bar. I want to keep connections with classical world, so I don't want to set h bar to 1. So you just see its momentum. Same if you do dilations, you will see dilation operator. So just the final thing about definition. I can forget about all this perturbation theory and will say that formally my psi n of lambda is equal to some unitary, which is function of lambda, times psi n of 0. So I'm imagining I have continuous unitary transformations. Then if I differentiate this with respect to lambda, this expression, I will get d lambda u dagger u times psi n of 0, right? So I'm just differentiating this whole thing. And I inserted u dagger u such that this gives me back psi n of lambda. And this is nothing but my a. So a lambda is related to basically derivative of the unitary. Okay, this is definition. So, and when we do perturbation theory, we essentially study properties of this operator. Wrong. Good. So now let me show maybe some examples where we see it. And I'll start from, again, a textbook example. We actually, for 5 or 6 years in collaborations, Marcus Riegel and Peter Klaes, we are writing a textbook on quantum mechanics, which we want to make as orthogonal to all text as others. And then we have to think about basically basic problems. And one of them is Bohr-Sommerfeld quantization. And I'll try to show how it's connected to adiabatic transformations. And the reason I want to say it is that in this way, I believe one can go beyond one dimension. So, and of course, I want to show how we can go beyond. Again, I'll just basically sketch the details, and then if you are interested in more, you can ask questions. So let me just look into generating function, just exponential of the Hamiltonian. There is no h bar, there is no time, it's just a generating function, right? And of course, I can write it formally as e to the minus I e n times projectors to eigenstates formula. That's true in all dimensions, right? And now let me take a Wigner transform of this. So just for those who never heard about this, this is sort of a way to convert operators into functions of phase space variables. It's not unique, but I'll stick to Wigner. So if you have any operator A, you define Wigner transform like this, I xi p over h bar, and you get a function of x and p. And for example, Wigner function will be this Wigner transform of Weil symbol of the density matrix. So now we can do the same for this generating function. And on the one hand, we will get e to the minus I eta h Weil transform. And on the other, we get e to the minus I eta en times Wigner function corresponding to a given eigenstate, right? So by definition, Wigner transform of this is a Wigner function of an eigenstate. And now you can sort of see where I'm heading. So this you cannot generally calculate exactly, but you can derive expansion in h bar. So I don't want to go into details. Let me just say, in the leading order in h bar, this of course becomes a classical thing, e to the minus I eta h. And then you can find Wigner function of eigenstate by multiplying by exponential and integrating over eta. And you see immediately that in the leading order in h bar, Wigner function of eigenstate is a microcanonical distribution. And that's, of course, we know that, right? So when we plot, I don't say WKB functions, they oscillate around whatever 1 over square root of v, right, which is becomes a microcanonical distribution. Good. So now I can, like one last ingredient, how we can go to Bohr-Sommerfeld, I'll use Hellman-Feynman theorem. Suppose I deform Hamiltonian in some way. And if I want to compute how my energy changes, you know that derivatives of eigenstates cancel, so I only need to compute this, and this is the same as integral over dx dp. Let's say I change potential, d lambda v times Wigner function of x and p. But if this Wigner function is microcanonical, I know that I conserve adiabatic invariance, right, in one dimension. So it means that integral of p dx is conserved. For harmonic oscillator, I can find this explicitly, right? I know this is 2 pi en over omega, which is 2 pi h bar times n plus 1/2. Now I see immediately for any adiabatic deformation of harmonic potential, this works in the classical limit because my Wigner function is microcanonical ensemble. So I proved you Bohr-Sommerfeld quantization without writing 80 functions, Schrödinger equation, boundary conditions, or anything. The key thing is adiabatic connectivity. If I go from this potential to this potential, my adiabatic conditions break here. So I need to find adiabatically connected system. So same, if you do infinite square well, you could also know energies. This integral of p dx will be 2 pi h bar n without 1/2, right? And then I can say any adiabatic transformation of this will give me conservation of this, right? But now the good thing that I didn't tell you how, but you can do h bar expansion. And let me give you just an example. If you want to go beyond this Born-Oppenheimer, again, it's a very simple calculation. You can do it in probably 5 lines. So the correction will be h bar squared over 24m d by dE g of E times V double prime of E microcanonical average. And if you do this, you can check, say, for quartic, where we did quartic potential. If you go to level number 3, you get factor of 1,000 improvements. And again, I want to emphasize that nothing here is related to 1D, except adiabatic connectivity. So in 1 dimension, classical adiabatic transformations are very simple. When we go to high dimensions, we have to be careful because harmonic limit, which I used here as a starting point, is integrable, but generic 2-dimensional systems are not. So I need to find a path how I go from integrable to ergodic regime. And I'll talk more about this. This path is non-trivial. Let me now switch gears, and I'll show another example, which is actually very much related to first lecture today. So it's about how we go beyond Born-Oppenheimer approximation, or how we can separate what is quantum, what is classical. Let me give you an example of some Hamiltonian. We have, suppose, p squared, some kinetic term, plus magnetic field, which, say, depends on x, coupled to some spins. Again, they don't have to be spins, but basically what I'm saying that I have some variable, which is, say, classical, right, and some variables which are quantum, right? Instead of spins, I can think about electrons' coordinates, and this will be ion coordinate, right? And then, of course, it's sort of an old problem how we describe, say, dynamics in the system, or equilibrium in the system. And the standard approximation is Born-Oppenheimer. So what it does, it tells us that we can find unitary, which diagonalizes. So in principle, we can have also, let me just say this, where this Hamiltonian is diagonal. So like in this case, it's of course unitary, which rotates us along the magnetic field, right? Then we say fast degrees of freedom adiabatically follow, for example, the ground state, or could be like even if it's thermal state, adiabatically follow the thermal state. And then we say that there is a classical Hamiltonian, which depends on x and p, which is basically the expectation value of psi ground state, H psi ground state, right? And this psi ground state and H are at given x and p. Well, here, of course, psi ground state doesn't know about p. So this is a standard approximation, but then one can ask how I can go beyond. Because this approximation is great, but it fails in most interesting situations. And there, actually, problems begin. Because if you want to justify this classical limit, you usually have to write path integral. So initially, p and x are operators, right? You write path integral, and then you take a saddle point. But here, if you write path integral with this beast, it's a matrix. So how to take saddle point of the matrix, we don't know. At least I don't know. So, and Born-Oppenheimer kind of helps you. It makes this matrix diagonal. But then you run into another problem, that eigenstates at different times don't commute, because by doing this classical approximation too early, you assume that x of t is time dependent. Moreover, when classical degree of freedom couples to quantum, you start getting quantum noise. So x of t is not a continuous function. And then you're even in a deeper trouble. And interestingly enough, the solution was found by a student at BU. He works with Anusha Chandran and myself, and I think it's beautiful. And this is really related to part one of my talk. So let's just notice that actually U of x is a generator of adiabatic transformations with respect to x. So, and the problems with sort of Born-Oppenheimer come because we take classical limit too early. And what Bernardo suggested, that actually let's do the following. Let's do first some unitary rotation of my Hamiltonian. In general, U can depend on both x and p. But let me just say some U. And after that, we will take Weil symbol. So Born-Oppenheimer, you first assume, Weil symbol actually means you convert x to variable x. Operator becomes a number. So the subtlety is in order. It looks like it shouldn't matter, right? But this is actually formally what you want to do. You first do unitary rotation, and then you do this Fourier transform, mapping operator x to symbol x. And then you get almost the same expression, but you need to diagonalize this object, where instead of a product, I put a star, a Moyle product. Again, my lecture is not about Wigner-Weil quantization, but let me just say how it's defined. So if you want to compute Weil symbol of the products of two operators, you get Moyle product, which is IH bar over 2 times lambda, which is a Poisson bracket. So this is the exact definition. That's where quantum mechanics is hidden. And in part one, when we were looking to corrections to Born-Oppenheimer, we were basically expanding in this Poisson bracket operator. Right, you can sort of immediately see that xp, for example, Weil symbol will be xp plus IH bar over 2, because if you put this down, derivatives will give you 1. Anyway, so, but then if you now say, okay, my Born-Oppenheimer is the starting point, but then I will start expanding in H bar, you'll immediately see that you will get derivatives of U, and they give you a adiabatic gauge potential. So what you find, perhaps amazingly, maybe not, that you find that beta H beyond Born-Oppenheimer, let's say BBO, so it will be p squared over 2m minus, well, I actually converted p to classical, but it doesn't matter, it can remain quantum. It's p ax plus axp over m plus ax squared over 2m. You might recognize your electromagnetism. So you basically get same expression as an electromagnetism, and one can say, oh, Berry got this. There is an important difference that this is an operator. So what we are doing is kind of doing Schrieffer-Wolff, integrating out low degree of freedom. And this is non-perturbative. Just, I'll say you in words, imagine that B rotates in space. Generator of rotations in space is, suppose it rotates in xz plane, will be sigma y, right, sy. So this term will be proportional to sigma y, and if you think about this, you'll kind of get a matrix which looks like B minus B. This is Born-Oppenheimer, and you'll get P d theta dx minus P d theta dx, I guess with i's coming from sigma y on off diagonal. You'll immediately get relativistic dispersion. This you cannot get in any order of perturbation theory. It just comes out from here. Another, actually, this turns out, this is related, this whole thing, to a like famous problem in mathematics, which I think is highlighted in the book by Lieb. And this is a piston problem. I don't know how it's called. Imagine you have particles here, particles here. You have a massive piston. The whole thing is isolated. You can create a state when your pressures are the same, but temperatures are not the same. How will it equilibrate? Right? So the whole system is isolated. Turns out it's like extremely hard problem. Anyway, so here what you see immediately is the solution to this problem, because this term is nonlinear. So now we actually heard about dilations. It's like what appears in pressure. So here are diabatic transformations of dilations. The adiabatic gauge potential is dilation operator. So you'll get contribution, which is difference of dilation operators xp here minus here squared. It gives you interactions. And we didn't check whether it gives you thermalization, but at least it gives you dynamics, non-trivial dynamics. OK. So the last thing maybe I want to mention more or less explicitly before going to chaos is going to moving frame. And this might be a way to, it opens sort of a door to understanding what's non-equilibrium systems, quantum control, state preparation, and all of this. And many of the things are actually used now experimentally. So now suppose I want, I'm not, so in Born-Oppenheimer, I'm assuming that my sort of this classical degree of freedom, or whatever slow is autonomous, it's kind of coupled. But when I do like control problems or state preparation, I say it's an external parameter. So let me assume that I have now some Hamiltonian which depends on time through lambda. And then I want to, for example, follow adiabatically some state or do something like that. So what I can do, I can write my wave function in a moving basis. I'll write psi n of lambda. So basically, I expand it not in fixed basis, but in basis which depends on lambda, which depends on time. That's equivalent of going to moving frame classically. When we sit in a car, in a train, and train accelerates, we want to solve everything in a moving frame, but we add extra forces like inertia forces and so on. Now, if I take time derivative of this, you'll immediately see there will be two contributions. One is derivative acting on this, and one is derivative acting on this. But I can use chain rule. So basically, I will get IH bar lambda dot times d by d lambda acting on psi m. But this is nothing but my adiabatic gauge potential. And I can move it to another side of the Schrödinger equation. And basically, what I will get, I dt moving psi is equal to h minus lambda dot d lambda times psi. Right. So basically, I can define moving time derivative. It's exactly like in classical mechanics. It describes motion of, my ball or whatever in a moving frame. Here, it describes motion of expansion coefficient in a time-dependent basis. And trade-off that I have to introduce this. So of course, for translations, this, as I explained, it's momentum. This is Galilean transformations. For rotations, it's angular momentum. You go to rotating frame. But this is generally always true as long as a lambda exists. And this will be sort of, whether it exists or not, will be sort of main subject of this talk. So now you can probably believe me, or maybe it's even many of the things I should know, that all non-adiabatic response is due to this, right? Because H, by definition, is diagonal in this basis. So it doesn't cause any dynamics. All dynamics comes from here. And then we can imagine that we heard about quantum Hall effect. It's non-adiabatic response. And A, well, expectation value of A is precisely Berry connection. Expectation value of commutators of A is Berry curvature. So Berry curvature appears as Lorentz force just by doing normal perturbation theory. In the same way, inertia force will appear. So if you have extra mass, it appears because of perturbation theory. But actually, it's much more than that. So if A exists, we know that my problem is controllable in a sense that I can do reversible processes at arbitrary speed. And this goes to so-called counter-diabatic driving. If I introduce in the lab this Hamiltonian, h plus lambda dot a, then in the moving frame, lambda dot a cancels, and I will have no transitions. So again, just to give you a simple example, if I want to rotate a spin, instead of rotating in spin, I can turn on magnetic field in perpendicular direction. It will rotate by itself. And exactly this is adding this adiabatic gauge potential. So now, of course, the question is when this A is local, or when I can approximate it with a local operator. Can I find a path in my parameter space where this is the case? And this is, if you think again about like everyday examples, if you think about diver, like soon there will be Olympics here, right? There will be divers jumping into water. They kind of implement counter-diabatic driving. They find a path such that they don't create splashes. So if you think about waiter, that's example with this we wrote in the first paper, waiter who wants to bring the glass. If waiter does it quickly, water will splash. But if waiter tilts glass a little bit, the water is much more stable. Waiter is implementing counter-diabatic driving. But when we think about quantum computation, we want to prepare ground state like quantum annealing. We either have to do it very slowly. Of course, because this, yes, that's exactly. You have to counter, you have to implement precisely this term, or I would say it's local approximation. Yes. But at least this is, waiter example shows that this is possible, at least in some cases, even in complex systems. And generally, there is a problem which path you want to take where local A does you a good job. And my student worked on it, and there are like very interesting but partial questions related to Krylov. I mean, everything is about Krylov space, but I probably won't go into details. So let me finish this introduction. Half an hour, that's good. So let me finish this introduction by saying that this adiabatic gauge potential is related to all quantum geometry as we know it. So in particular, there is a quantum geometric tensor. So the parameter lambda could be multidimensional. I have different controls. Very often it's thought about as components of vector potential. Then it's related to currents, conductivity, and so on. But in general, it could be anything, magnetic field, interaction strengths, and so on. So generally, I can define chi alpha beta as sort of disconnected correlation function. It's basically overlaps of derivatives of these operators for each eigenstate. And then I can average over eigenstates with some weight. I'll talk later about this. And essentially, this object was introduced by Provost and Vallée in 1980. They called it quantum geometric tensor. Technically, they defined that you divide it by h bar squared. But if you want to have well-defined physical response or classical limit, you don't do it. But anyway, h bar is a constant. So this object defines overlap of eigenstates. So it's kind of sensitivity of eigenstates, how quickly eigenstates change. And of course, this is sort of my path to chaos. But imaginary part of this is Berry curvature. It defines all this topology, like topological insulators, whatever, quantum Hall, I guess. Real part is called quantum Fisher information, fidelity susceptibility. It's also related to mass renormalization, speed limits, and many, many things. OK. So it was probably a bit quick, but I want to now sort of slow down. And I will discuss relation of these objects of, if you want, eigenstate sensitivity and low-frequency noise. Adiabatic should be related somehow to small frequencies, long times, right? So I want to relate this object to chaos, basically ergodicity, and integrability. If there are any questions, if not, I'll continue. Okay, I think I can now erase this and start over. So basically, again, of course, historically, what we were doing is not how I presented. It was more like a random search, but then once you notice something and things start making sense, you actually realize, oh, it's very natural, it's very simple, very like elegant, and so on. But essentially, the student who worked on this, he graduated by now, Mahit Pandey. For him, it was a 2-year like random search project. He was searching basically in that direction, and things didn't work out, and so on. But then we realized we searched in the wrong place. And then accidentally he found something, and then sort of it started. And sort of my entry with this to MBL was because we just finished this work, and then we wanted to see what's going on in disordered systems. So what I want to do now is to relate this adiabatic gauge potential and its measure, basically how big it is, fidelity susceptibility, to physical properties. Because I told you that if this adiabatic gauge potential exists, like I can do many wonderful things, but it's more or less clear that in chaotic systems you cannot follow adiabatically eigenstates. So what am I talking about? But I mentioned example of the waiter. Like we have a chaotic model, and yet we can do this. So it means that many things don't exist exactly in physics, like mathematically they will define. But if you define them in the right way as an asymptotical limit, then actually they behave much better. So I'll get back to definition I started from. So now I'll try to go a little bit slower. So stop me if I'm too fast. So again, think about adiabatic gauge potential as a Hamiltonian which adiabatically moves me between eigenstates. So it's Hamiltonian which defines adiabatic evolution of H. So if you want, it's kind of complementary to H. H sets me the ground state. For example, I'll talk about ground state for simplicity, but I'll talk about any state. Anyway, H sets me eigenstates, and A tells me how to follow these eigenstates. So it's sort of like a dual object. So now I will start getting rid of energy denominators and eigenstates. At the end, they are language, and for large systems, it's not very appropriate. So let me notice that if I multiply both sides by EM minus EN, then I can rewrite this as I H bar and d lambda H M is equal to N minus N commutator of H and A lambda.
Just for that, you're still assuming that there's no degeneracies throughout?
No, because you see, I mentioned unitary transformations. I assuming there are continuous transformations, but very soon I will introduce time regularization. So degeneracies don't matter. Degeneracies, if they are like symmetries, they lead to important consequences. Like this A can become block diagonal between different blocks. So, but for now, the only thing I'm assuming that there are continuous unitary transformations. I use this language because it's sort of easier to show, but this is not important. But degeneracies, if I think about points where Hamiltonian has macroscopic degeneracies, that's where we'll get divergences of A, and that's all physical and so on. Anyway, so I can say that basically this is equivalent of saying that for any NAM, my d lambda H plus I over H bar, I think sign is wrong. Anyway, I just remember this equation by heart, so I'll write it. Lambda times H m is equal to 0 for n not equal to m. Right. So this looks like this operator should be equal to 0. But that's not actually true, and that's not surprising that I call it adiabatic gauge potential, because you can see that A is defined up to commuting terms. I can add anything which commutes with Hamiltonian, and this doesn't change. And for this reason, A cannot change diagonal elements of H. Because if I put n here, then expectation of commutative with any operator is 0. So it means that this part can only contain diagonal elements. But then I can say, well, it means it commutes with H. So it actually means that this operator, G lambda, is a conservation law. Here I get basically first non-trivial result. So first I can say, then this is equation which defines A, and now you can see I kept H bar and I. For classical limit, this becomes Poisson bracket. So again, everything is well defined so far in the classical limit, at least on the level of equation. And then I immediately see that if I have local generator of adiabatic transformations, I must have a conservation law. So you can think about this as extension of Noether's theorem. Noether's theorem tells me about symmetries. Symmetries are special adiabatic transformations which don't change spectrum. You can define a symmetry as a adiabatic transformation which doesn't change spectrum of Hamiltonian. And then we know there are conservation laws, right? This is Noether's theorem. So A itself is conserved, of course. But I can talk about adiabatic transformations which do change spectrum. And as long as they are local, I have associated conservation laws. And it immediately already hints you that adiabatic transformation should be related to integrability. And it's actually a very interesting exercise. It was done by two Japanese people, and we played with this. So if you just take a particle in one-dimensional potential and ask for which Hamiltonians this equation has a closed form solution, when A is a low-degree polynomial in momentum like P cubed, you immediately get Korteweg de Vries equation. So this becomes equivalent to inverse backscattering methods in mathematics. Why, I have no idea. But if you do this exercise, and then I think that you can actually go beyond. It's not, you can. No, it works in any D, but then I'm honestly waiting for a good student to try to play with high-dimensional examples. It's clear that if you go to 2D, you really have to couple your momentum to vector potential. So there is no.
This is more generally inverse scattering method, is what I'm trying to say.
Probably, and here, you can allow for arbitrary deformations of the spectrum. So like, for example, in 1D, when you ask what it means this commutes with Hamiltonian, you can say it's a polynomial in Hamiltonians. And you stop in some order, and you get self-consistency equations. If you go to orders larger than 2, I mean, order 1 is energy shift. Order 2 is squeezing of energy dilations. That's where you get Korteweg de Vries. If you go beyond, you can get highly non-trivial transformations. I'm not a mathematician, so I don't really know how useful it is, but at least for me, it's much simpler. Inverse backscattering method is so complicated and so fine-tuned to my taste. This is like very, very simple. Okay, so right. So we see this, right? So immediately we know that for integrable systems, I should have at least n integrable directions. So the other thing which I will mention but will not emphasize today, this is important for control and so on. So if you look into this equation, look closer, then you can see that you can obtain it by minimization principle. And where we have minimization principle, we can develop variational methods. But this is variational methods for operators, not for states. So you can apply them again to classical systems or thermodynamic models and so on. So what you can say is that if you define an action, which is basically trace of some arbitrary density matrix times G lambda squared, this operator, and you minimize that. So rho is important saying it commutes with the Hamiltonian. So think about this Gibbs distribution. If temperature is 0, this is ground state. If temperature is infinity, just trace, right? It can be any other function of energy. So if you minimize this with respect to A, you will get the right answer. And I can give you proof without writing any equation. So as we discussed, so A here attempts to remove all off-diagonal elements. It cannot touch diagonal elements. So clear this norm is minimal when this G has 0 off-diagonal elements. So it means that if I minimize this with respect to all possible operators, I'll find exact equation. And of course, there is a little bit of degeneracy, because if rho only projects to the ground state, you'll find A which only works for the ground state. But as long as rho exists everywhere, exact minimum is always the same. But of course, when you define variational approach, this rho can bias you towards energy spectrum you're interested in. You can choose microcanonical and target specific energy. You know, physics is different at different energies, right? You can have phase transitions, a function of temperature, and so on. So this is basically your, if you want, target function. And this is exact, I will relate this shortly to spectral functions, so on. That's exactly the same rho which appears in your physical response. So that's why I like Gibbs distribution. So, and then variational principle, how it works. Well, you just take operator ansatz. You can take local operators or physically motivated operators, like we do with any variational approach. But you start thinking about operators instead of functions, right? And then you minimize within this ansatz. And if you're lucky, you'll get very good results. And what actually some people found is that particularly, first was actually Peter Kleis, who noticed that particularly good ansatz will be if you work in Krylov space. Okay, and I don't really have time, actually have experts here on Krylov space. It's basically a space where you expand your operating in powers of commutators with the Hamiltonian. So if you work in this space, you find extremely good variational ansatz. And that's how physics works, that's how locality works. So by the way, there were many interesting mathematical talks, like existence of this, I think it's extremely interesting and open problem under which conditions it exists and so on. Anyway, but let me now move on. So I mentioned about connections to classical physics, but now I think I will spell it out explicitly. So this A lambda has a well-defined meaning classically, and this is generator of trajectory preserving canonical transformations. So, you know, it's like in any book in classical mechanics, if I write dx d lambda is equal to minus dA dp, and dp d lambda is equal to dA dx, right? For arbitrary smooth function of A, I know that what I'm doing canonical transformations. If you want, if lambda is time, A is minus Hamiltonian, then this is Hamiltonian evolution. But this works for any function, right? So, of course, if I think about translations, x goes to x minus lambda, then A is P. So in classical physics, like in quantum, P generates translations. Angular momentum generates rotation, so it's the same story. But now I can ask, which canonical transformations will not change my trajectories? In other words, I will ask, can I change my canonical variables such that they will basically mimic change in the Hamiltonian? we know, again, for translation, it's very simple. I shift the box. What shall I do? I should shift my coordinates. I squeeze the box. I squeeze my coordinates, right? But suppose I do it more generally. I have some transformation, and I ask, can I do infinitesimal change in canonical variables such that essentially up to commuting terms, which are sort of frequencies of rotations, I will get 0. I will get the same result. So if I do this, just believe me, you will get exact same equation. You will get d lambda h minus a lambda h Poisson bracket h is equal to 0. Okay. So now back to integrability. So yes, before going to chaos, let me actually say one more thing about integrability. So I just told you that A is a generator of unitary. And now I told you in integrable models, we must have n is number of degrees of freedom, integrable directions. But let me actually say that it's interesting that it's enough to have one integrable relation to preserve integrability of the model. And this follows from this observation that because A is a generator of unitary, I know that my unitary, it's now, just replace time with lambda, h with A. So you know the answer. So my unitary is path ordered integral. I, again, don't remember science, but it doesn't matter. Right? So because A is a generator of unitary transformation, it means my unitary is a path ordered integral. Now, you see, role of time is played by lambda. So if I do finite change in lambda, and if A is local, it means that unitary is local. I assume there are Lieb-Robinson bounds and so on. Again, bosons, whatever, like, I'm not trying to be rigorous from this point of view. But at least we know in physics that as long as this is local object and you have finite time evolution, this is local. Sometimes people say quasi-local. You can get like exponential tails, but it decays. Now, if you have some conservation law which commutes with original Hamiltonian, then obviously this Q, which is equal to U dagger Q naught U, will commute with my deformed Hamiltonian. And if U is local, it means that I preserve my conservation laws. So it basically tells me that if I just repeat what I said, if I have one direction, one coupling along which my adiabatic transformations exist, it means I keep model integrable. I preserve all integrals of motion. And I mentioned this is related to Schiffer-Wolff transformation. Usually one writes that this is e power s. Sorry, it's not action. It's now a generator of Schiffer-Wolff transformations. And so you immediately see relation between S and A is like relation between Floquet Hamiltonian and time-dependent unitary. So, but I would argue that A is more convenient. I mean, if you do perturbation theory, it doesn't really matter. But if you want to do something more sophisticated, A is more convenient. You can do variational approach. And moreover, you can define path-dependent Schiffer-Wolff transformation. And in some cases, it's super important because I'll mention in the end, when you're close to integrability, it's very important how you deform Hamiltonian. So this A might be like ill-defined along some directions. Okay. So we covered this. So now I guess the last thing I need to cover before I go into chaos is the relation of A and dynamical response. And I will use again exact same definition I use many times. So A lambda and M would be I H bar and D lambda H M over M minus EM. So now you probably all know that this awfully looks like a principal value of integral if I put e to the IHT to the minus IHT. So, but when we define principal value, we have to take infinite integrals, and those are not always well defined. And so what I want to do, I want to introduce a cutoff, time cutoff. That's exactly what we always do when you have a diabatic limit, introduce some small epsilon and so on. But I really don't want even to take the limit of this cutoff to 0. It will be my physical parameter. So I want to write this as IH bar and D lambda H M. And by the way, it's actually good that you have H bar because this becomes frequency, and frequency is what we have in classical physics. Anyway, I have E n minus EM, EM minus EN, divided by EM minus EN squared plus mu squared. So mu will be my inverse time cutoff. It will be my time scale. So if you want, if I want to get exact AGP, I can always take limit mu goes to 0. But here I'm cheating on mathematics. Instead of asking myself whether this limit exists, and actually in many cases it does not, I will ask what's the asymptotic behavior of AGP as mu goes to 0. Physically, this will correspond to what is sensitivity of my eigenstates when I kick them out with energy difference larger than h bar mu. And classically, it will mean that can I construct canonical transformations which map trajectories to each other up to time 1 over mu. So it's very, very physical cutoff. But now, with this mu, this object always exists. There is no problem with small denominators. There is no problem with degeneracies either. So they might show up when I take limit mu goes to 0, but they don't play a role, like in terms of convergence. And this object will be equal to, actually, let me remove h bar. I think it will be 1/2 integral from minus infinity to infinity dt sine of t e power mu t d lambda h of t. I mean, of course, strictly speaking, I also need to take matrix elements. And this is my Heisenberg evolution operator, which is equivalent to just classical evolution of my perturbation conjugate to lambda. So instead of like doing this derivation, let me just say how it works. The sine of t makes sure I get principal value, delta function cancels, right? And then if you use this Lemon representation, you'll get something like IEN over h bar t minus IEM over h bar t. You integrate, you get this. Right? So in this sense, this conservation law would be nothing but quasi-particle residue. Okay, and I skip algebra, but if I write the answer, you'll say, of course, this has to be the case. And sometimes this is how we define quasi-particle residue. We just say, let's just create particles. So in this language, it's a field coupled to electron, right? So, and then you wait until the rest will disappear. And this is also, by the way, definition of Lioms. If I have time to say something about MBL, that's how Lioms are defined in MBL. So you start from some operator, say sigma z, you evolve it in time, and you say whatever is left is your sort of integral, your conserved operator. the integral of motion.
So can I keep this a little bit also as if I were to do some non-Hermitian thing, because it's just so good to have an imaginary component on the energies, taking the real part of that. Would that apply to some non-Hermitian?
I didn't think about, yeah, you can definitely do it. It's absolute, look, it could be equivalent because in a way, this cutoff, you can say, yes, it's a small dissipation, small imaginary part. So yes. Maybe it's equivalent way of you just saying that let me introduce I mu over 2 energy for each n. And maybe you can even take mu n dependent. I don't really know. But I think you're right. Yes, so basically the conservation law is sort of time average of my Hamiltonian. And then you see that I basically told you that if I have integrable systems, there will be always some, not always, but usually some overlap. If this is non-zero, some overlap of your deformation with these integrals of motion. Okay, so now you can sort of see that my A is related to time integrals. And the final thing I want to do is to introduce chi, which is basically sum over m not equal to n, rho n, and then I have n a lambda m squared. So this is basically sum over fidelity susceptibilities weighted with the same rho. So rho again could be Gibbs. This is your physics. And then I will use this definition. So this is the same as sum over rho n omega n. I will switch to this notation because it's more suggestive. Omega nm is energy difference times n t lambda h m. And for those who work with ETH, though ETH is not really important there, but let me just write an answer, and then you'll probably believe me, or we'll see where it goes. This is nothing but, integral over d omega, omega squared, over omega squared plus, I think I call this mu, plus mu squared times spectral function of omega. And finally, we have relation to noise. So phi of omega is nothing but 1 over 4 pi, sum over n d lambda. So this is what's known as noise or symmetric correlation function. Basically dissipation and my Kuba response, and so on and so forth. So again, you can see, or maybe it's even obvious if you go to Lemon representation, when I use symmetric correlation functions, I will get delta functions of En minus Em. So, and then when I substitute delta functions here, my omega will become omega Nm. Oh, it's En minus Em over h bar. Sorry, I forgot to say. Again, I wrote it in a way that everything here is defined in the classical limit. So I use quantum language. Of course, my phi will be different for quantum and classical systems, but on operational definition, quantum mechanics plays no role, right? And now, this is, I would say, the main result, and I will jump straight to chaos. I don't know how much time I have. I have 25 minutes, right? Okay, yeah, this should be enough. So I just want to emphasize something. So this left-hand side chi is expression which tells me about sensitivity of eigenstates to small perturbations, or alternatively, complexity of generator of trajectory-preserving canonical transformation. I forgot to say that in classical language, chi is equal to integral over dx dp over all phase space. It's multidimensional of basically my rho of xp times a lambda squared of xp. It's exactly the same definition, but I integrate over phase space instead of summing over eigenstates. It's the same thing, right? So in a way, chi tells me about how complicated it is to map one trajectory to another, right? Finding this canonical transform is very difficult, but finding complexity is easy and moreover experimentally measurable, because these are objects which appear in experiments all the time. It's your Fermi golden rule rate, dissipation, whatever, fluctuation dissipation theorem, noise, and so on, right? So, and now look what happens. This complexity is related to low frequency noise. Just want to highlight, nothing changes in time here. Here I ask about static object, which is what's the complexity of my canonical transformation? I'm not doing anything. I'm just asking, what would be complexity of transformation if I do small change, right? On the right-hand side, I have equilibrium spectral function, right? So this is equilibrium response in my thermal equilibrium of operator conjugate to H. So, and now I see when mu goes to 0, this is 1 over omega squared. So what I see is that low frequency noise tells me about complexity of these transformations. And this is actually sort of my punchline of how it's related to chaos. We can now intuitively imagine that if the system is chaotic, I do a small change in the Hamiltonian, and my trajectories will change completely. Both. And there is no difference. So what I want to say, there is no difference between quantum and classical chaos. I'm not joking. There is basically bad definitions of chaos. Bad, I mean, not applicable. One defines classical chaos through Lyapunov exponents. One defines quantum chaos through random matrix theory. And this is even incorrect. Because if I take, I don't know, two-dimensional nonlinear system, it can be as chaotic as one can imagine, but you will never see random matrix statistics. So random matrix statistics is ergodicity of mixing. Chaos is different. Yes, usually mixing comes with chaos, but inverse is not true. And actually, for classical systems, this was noticed a long time ago, that if you go from integrable regime to ergodic regime in between in this KAM regime, you have super slow dynamics. And the reason is that you kind of have a levy flights between integrable regions. And they, at least, I'm not familiar with all the literature, especially mathematical literature, so I might miss something and so on, I apologize. But my take from this, it was noticed as an observation. Oh, by the way, we noticed slow dynamics. What I want to say, this is really, slow dynamics is really a signature of chaos. And one can even define chaos like this. And I don't know, we tested it in all possible systems we could, like now tens of them. It always works. Like how to prove things, I don't really know. Now let me just say that I'll basically speculate. So usually if I give like talk with slides, I show some numerics. Here, let me sketch numerics, like what happens. And then if you are interested, I can show you later real pictures.
So is your statement that sort of looking at the spectral function and its low frequency behavior, that distinguishes either classically or quantum mechanically whether the system is
Yes.
or not?
Yes. Moreover, it will distinguish whether the system thermalizes or not. So let me now tell.
Can you specify what the type of behavior is?
Yes, that's what I'm going to do right now. Yes, exactly. So now I'm going a bit to like uncharted territory. Yeah, I talked to some mathematicians and quite a few, and they couldn't help me. But we can analyze some simple examples. You can analyze like analytically and so on. So let me just show like typical examples. So I will plot now a spectral function, phi of omega, as a function of omega. So say it's log-log. It's positive both. So in this sense, I kind of blow up low frequency regime. So let me start from integrable models. So there are, of course, integrable models which are, I don't know, we know like in quantum mechanics, transverse field Ising model or gapped systems. So if they are gapped, they just have hard cutoff. So phi over omega is just 0. But what happens for generic integrable models? Again, we have one example. It's like two-spin model where you have two classical spins Sx, Sy, which interact with anisotropic interactions like Jx, Jy, Jz. This model was studied to death. So there, I think one can even get analytical results. We got them only in XXZ limit, but most things are known. So what you have is spectral function goes as omega squared to small omega and so on. And this omega squared we found also in quantum XXZ chains and in many other models, central spin models and so on. So this omega squared seems to be very, very robust. So at small frequencies, my spectral function goes down as omega squared. There is actually a simple intuitive picture why this happens. What is integrable? And by the way, for integrable model, it's important to have integrable deformation. Otherwise, this is wrong.
And it's also independent of dimension.
It doesn't. Yeah, doesn't matter. So what matters is where it starts. So it usually starts when you start feeling the boundary. So this could be something like ballistic scale, Townley scale, but in extended systems, so this is of the order of 1 in non-extended systems. So basically, heuristic reason for this is very simple. So if I think classically, my integral motion is motion on the tori. Now I ask, what is the probability that frequency is 0? And you immediately realize it should be small. Because most toris are like, it's some kind of parabola, right? I have some potential with some minimum. When I have parabola, my frequency is never 0. In order to have 0 frequency, I have to fine-tune my tori either to this situation or to this situation, something like that. So here I can get infinite period, 0 frequency. Or here I have infinite. But these are kind of measured 0. So again, this doesn't tell me why it's omega squared, but at least it tells me that it's hard to find small frequency tori statistically. But as I said, in XXZ chain, you can say, oh, these are my gaps. And my gaps, I have gapless excitations, and then density usually goes to 0. Anyway, I'm talking, by the way, on gaps on the scale of many body levels, not single particle gap. OK, so integral models, we always see the omega squared or something faster than omega squared. So what about ETH? So by ETH, I mean ergodic systems. We actually know the answer. Because phi of omega is roughly off-diagonal matrix element times the density of states. Center of mass, I don't know. So if we have ergodic systems, this is exponentially suppressed, this is exponentially big, this is finite, like my spectral function. And random matrix theory tells me that this is constant. So if I have random matrix models which are ergodic, then typically there is a Townley scale, which is classical. It's usually diffusion constant over L squared, but I mean, if I don't have, a zero-dimensional system, it's something else. It's a basically scale where random matrix theory appears. And beyond that, my spectral function is constant, which basically means that my chi behaves as 1 over mu. It's interesting, and then there is something here. But it's interesting that I can get the same behavior from just hydrodynamics, which actually tells me that, or at least indicates, maybe I'll use less strict term, that random matrix theory is related to hydrodynamics. So let me just take very simple diffusion equation. So suppose my observable is n, means lambda is, say, electric field on this side, potential. So it's d times some Laplacian n, right? So it means that my n will be sum over k, and k times e to the minus So dk squared times tau, right? So this is a standard solution of diffusion equation. Don't worry about boundary conditions or anything. Just simple-minded. So if we wait for time which is larger than t tau-less, which is L squared over d, all exponents decay are very small. So I'm dominated by smallest exponent, which means smallest k. So this means that this is approximately equal to n1, just this 1 means smallest k, smallest momentum available, times minus t tau over t tau-less. Or maybe I'll just write tau times omega tau-less. So if I take Fourier transform of this, my phi of omega, it's just Fourier transform of n, right? It will be something like omega tau-less over omega tau-less squared plus omega squared. And this saturates at small frequencies. So you can say, oh, this is a coincidence. There are many functions which are constant. But look, it's the same scale. It's the same omega tau-less which appears in random matrix theory when people study spectral form factors and so on, and the same omega tau-less which appears in diffusion equation. And in both cases, I expect my phi is constant and my chi divergence is 1 over mu, and that's indeed confirmed numerically. So I can say that asymptotical behavior of chi is 1 over mu indicates ergodicity. It doesn't prove ergodicity, but at least it indicates it. And the most interesting thing, and it was very surprising to us first, but then of course we realized that that's how it should be, is that if you just break integrability, again, it doesn't matter whether the system is quantum or classical, low dimensional, high dimensional, you kind of same have behavior. So you go from this to this. And this is the naive assumption that, well, this just starts increasing. And this was, I will tell you, this was exactly the main mistake in this RG paper by David Hughes and others on MBL. And that time it was subtle. They made this assumption, and if you make this so it continues to go from this to this, the RG works. But the reality is that here we also have Drude weights. We have delta functions. That's exactly why my system is integrable. So these Drude weights are basically my leftovers, my conservation laws. And when you start breaking integrability, you actually start broadening these Drude weights. So instead of going continuously, what happens is that you develop tail in the spectral function. And then we did some numerical work. There is a lot of universality here. You can do finite size scaling. Transitions to integrable behavior, they behave almost like continuous phase transitions. You just do finite time instead of finite time scaling. You get various critical exponents. We don't understand them. But essentially, this is what people call subdiffusion exponents. Right? So, and the point is that quantum mechanically, this will stop when omega is of the order of Heisenberg level spacing. Classically, it doesn't stop generally. And so now what happens if you go into these KEM systems, which have this chaotic but non-ergodic regime? This asymptotic behavior lasts forever. There is no other scale. And then what, again, we observed numerically, this power is arbitrary, so it depends on integrability breaking. But if integrability breaking gets smaller and smaller, of course, this tail occurs at smaller and smaller frequencies, but also the power approaches 1. So you get something like 1 over omega. And 1 over omega is the largest power we can possibly have, because integral of spectral function is the basically variance of your operator. In your eigenstate. I mean, it's a sum rule, which you integrate over frequency. So it's finite. If you want, it's like sum of all of diagonal elements squared. So this is a sum rule. And you see 1 over omega is the basically it's a power which separates divergent and non-divergent integrals. And interestingly enough, this is exactly 1 over f noise. It's like super old problem of where it comes from. And it turns out that in many cases, now I can say safely, including MBL, whether it's quantum and classical makes no difference. If you analyze classical disordered system spin models, they behave in the exact same way. So you develop this 1 over omega. If you take, there are many examples which show this 1 over omega behavior, but not all. And this is like we talk about open problems. One of them, how we classify integrability breaking perturbations. And there are some ideas in quantum chaos, classical chaos literature. Maybe I can talk during discussion. But essentially, maybe I'll take connection to MBL. There are very special perturbations or integrable points where Hamiltonian is sum of commuting terms. That's what happens, for example, with disorder. Again, it doesn't have to be disordered. You can take any incommensurate spectrum, whatever you like. And then if you start breaking integrability, so integrals of motion are trivial. This is just magnetization on each side. If you start introducing local network by hopping, then within any order perturbation theory, you cannot normalize. Because within first order, you can hop only once and so on. So immediately see that you should get non-perturbative results. And non-perturbative really, numerically, it is associated with 1 over omega. But there are, as I said, there are many other examples where perturbation theory seems to fail. So what is sufficient, what is necessary, we don't know. In some cases, you get 1 over omega squared, but it's only transient. So it's like Fermi golden rule rate. There is another short time scale, and so on. So yeah, I'm closing to the end. So let me now just describe why this is sort of related to chaos, like pictorially. So and I'll again use classical example because I think it's more intuitive. So quantum mechanically, as I said, we look into sort of sensitivity of eigenstates, but it seems like completely quantum. Now let me think classically. So normally what we do, I know, we send two twins to the room, right? And give them slightly different kicks to the butt, right? And they start moving chaotically. And then we see how their trajectories separate. So that's kind of standard view on classical chaos. So what we are doing here is somewhat different. We have two identical twins, two identical kicks to their butt, right? But we have slightly different rooms. And then we ask how their trajectories will sort of change because of this, right? And by change of the trajectories, I don't mean their separation in time. This is ill-defined. What I mean is that how difficult it is to reprogram my kid such that this kid repeats the trajectory. So it's a slightly different way in chaos. And then you immediately see why, I'm coming back to turbulence, why weakly non-integrable systems are more chaotic. So what happens is that if you are integrable, you just change your Hamiltonian a little bit, you'll get slightly different trajectory. They are very close. Even if you don't know canonical transformation, you see it in me, oh, you need to squeeze here, you need to squeeze here, so it's more or less clear what you should do. When you are completely chaotic, well, you are divergent. I don't have any intuitive picture how to explain 1 over mu, but essentially the longer you wait, the harder it is. But if you, in between in this KM regime, it turns out that your trajectory is kind of, you are stuck in integrable region, then go away, stuck in another integrable, you do Levy flights. So you spend like very, very random time here with very long tails. So that's the reason of this slow dynamics. And then if I slightly change the room, you'll see totally different trajectory. But it's more different than just going exponentially because you are stuck for different long times around different points. And in a way, the system is becoming more chaotic. So if you want to relation in turbulence, as I said, this phi is related to dissipation. We also know, of course, turbulent systems, they are bad, they are dissipative. So, yeah, I didn't have time to talk about MBL much, but let me just tell you the story which seems to emerge. And both, as I said, classical and quantum disordered models. So in thermodynamic limit, everything indicates that eventually systems will thermalize. So eventually they will become ergodic. But yet what I want to emphasize that all this stuff, it makes perfect sense, but finite size becomes finite time. So what is true asymptotic behavior for finite size systems with few degrees of freedom becomes transient behavior if I have finite time systems. So if I develop like 1 over omega, eventually it will have to saturate. Well, integral of 1 over omega formally diverges. And this suggests that if I just impose the sum rule is constant, and phi behaves as 1 over omega, you immediately see that there should be a cutoff, omega tauless, which is basically exponentially suppressed in my integrability, inverse integrability breaking parameter, which is called J. And this what seems to happen. So I have super slow intermediate regime, call it glassy regime. Now, why this cannot last forever if I modify, see, 1 over omega is tricky. I modify it one way, I make integral slightly convergent. I modify it another way, I make it divergent. But this is another story which I basically wanted to say, but I think I don't have time. It's related to Krylov delocalization. So essentially, delocalization in Krylov space. So if I have local interacting models, basically, Lyom's unstable. Yeah, as I said, I don't have really time to talk about this. But anyway, so this picture seems to emerge. It's exactly the same if I do this classical model. And let me finish by saying, basically writing or trying to sketching like general integrability breaking diagram, which seems to occur everywhere. So if I have here a scale, which is, let me just take thermodynamic limit. I will say here I have scale log of 1 over mu. Again, mu is my cutoff, it's my waiting time. And here I will say it's roughly log of integrability breaking perturbation. Then what I will have, if integrability breaking perturbation is very small, I leave an integrable region. And usually, the longer I wait, the smaller the perturbation I need to see chaos. And that, of course, is consistent with our expectations. If I take gas in this room with very, very small interactions, I won't see any turbulence for very long times because it will behave as if it's non-interacting. I cannot have instabilities. So say my spin chains. And this is actually a good story because integrable systems, they have finite A, they're good for quantum control and so on. For finite times, we are good. We just need to make sure that we are sort of in this regime. But after that, I don't get ergodic phase. I get sort of a KM phase. And this is phase which cannot be described by thermodynamics. Again, think about turbulence, and people call it pre-thermalization or whatever. This is the system where I'm neither integrable nor thermal, even locally non-thermal. And then eventually, I might get to ETH. In low-dimensional system, this might go to asymptotic value, and there is a finite threshold. In many body systems, it seems that it all goes down, but there are very, very different scales. So there is always like parametric separation. How big it is, I have no idea. So this would be, basically this is like a KM threshold, and for chaos threshold, at least in classical systems, it's 0, but it really depends on the waiting time. So this usually goes, yeah, okay. some power of mu, I forgot. Anyway, so if you look into chaos in this way, you see that A, it's first of all, it's a function of time, and B, you see that it's sort of a well-defined concept, and if you want, irrespective of number of degrees of freedom, it seems that there are traces of KM theory in any dimensions. Again, I'm not a mathematician, so don't tell me this analogous KM is only comes from comparing the slow dynamics in systems where KM exists, and I know many body systems. It looks really identical. There are some subtleties, but yeah, essentially it's the same. So basically it's chaotic. In a way, it's a maximally chaotic regime because I forgot to say that here chi diverges is 1 over mu squared, right? Because phi of omega gives me extra power of 1 over mu. And then we have a TH regime. And again, this is like in phase transitions. Chi has a maximum. So you're not surprised. I mean, you have specific heat, right? We go from one phase to another. There is a maximum in between. So in a way, this you can call as adiabatic complexity or whatever. It also has a maximum. OK, I think I will stop here. I apologize. I have 2 more pages on MBL. But if you are interested, we can talk more about this during discussion section. Okay, thank you.